So hello, I'm Attila Sulyok, and basically I will continue Daniel's talk about this parallelization framework which can parallelize unstructured, so codes on unstructured meshes. I will present some optimizations that can be applied on GPUs specifically. These include using the shared memory as a sort of programmable cache, using two-level coloring, and developing a new algorithm that is based on partitioning and that effectively reorders the threads so that the memory locality is higher. We used the NVIDIA CUDA framework for the implementations, and we tested our algorithms on Pascal and Volta hardware. All my numbers will be from Pascal, but basically Volta behaves the same, just faster. So an unstructured mesh is just a collection of sets, edges, nodes, and cells or faces if you're in 3D, and connections between them that are called mappings. These map from the elements of one set to the other set. And when you have a loop or a kernel that iterates over the elements of one set, then you will, for example, the edges, then you will access directly the elements of that set, for example, here the edges, and all the other data indirectly through one of these mappings. That means that the access pattern is known only at runtime and can be highly irregular. These codes are usually memory bound, so the main performance bottleneck is the memory bandwidth. And we can improve the bandwidth by increasing data locality, either by increasing the spatial locality, which means that the consecutive threads need to access consecutive memory locations so that the cache lines are utilized effectively, or the temporal locality, which means that the data reuse is high, so one piece of data gets reused more than once in the same thread. We tested our applications on 5 different sample codes that are representative of their respective organizations' internal coding culture and coding style. These are mainly 2D and 3D computer fluid dynamics codes. Now, what we first want to avoid when doing parallelizations is the data corruption by concurrent increases. And the first way to do that is to use atomics. But these are slow, especially in older hardware, which don't even have hardware support, for example, for double precision atomics. The second way is to use large helper array, so that when the intermediate results are calculated by the threads, then these will get placed into the array at separate locations corresponding to that particular thread. And then we do another kernel launch, which will gather all these results into one, and that will be your final result. The problem with this is also irregular access patterns. Your intermediate results, so the intermediate writes, will be spread far out in memory, and you will have poor locality. Also, you will have to allocate a large chunk of memory in your device just for that array. Third approach is to use coloring, so that we color the threads so that no two threads accessing or increasing the same piece of data will have the same color, and then scheduling the threads so that the colors will get executed one after the other. And the straightforward way to do this is the so-called global coloring, where you color every thread, and then you, for example, schedule them into different kernel launches. And this way you have a correct result, but your effective data reuse, so you have no data reuse, your reuse factor is 1. In this case, if you launch the red color, then you will have to load every cell data into the... so you have to fetch every cell data from the global memory. And an optimization on that is to use the shared memory, which is faster and closer to the... the latency is lower. And to do that, basically you have to, before the computation, you prefetch everything from global memory to shared memory, do the computations there, and then after the computations are done, you write back into global memory. there are 2 points where data races can occur. First, when the blocks write back into global memory, so you have to color the blocks. And secondly, when the intermediate results get written back into shared memory, so you have to color the threads within the block as well. And this second one, the block coloring can be scheduled by kernel launches again, but the threads will have to be synchronized by an explicit sync threads operation. That means that the more thread colors you have, the larger amount of synchronization you will have in the kernel. But this means that when you, for example, you execute block 2, you don't have to load everything into memory. You can reuse some of the data, and you only need to load 8 cells worth of data. On airfall, we can see concrete numbers. For example, this means that from 71 gigabytes per second, the bandwidth increased to 227 gigabytes per second. Just this improvement. And this is how it looks like the original mesh of airfoil using this block coloring technique. Now we can see that the blocks are sort of long and narrow. This corresponds to the original numbering of the mesh. And the data reuse within them is not as high as we want to be, as could be. What we want is to increase the data reuse within the blocks. So basically, we want to decrease the data reuse between the blocks, and that gives an idea of using a partitioning technique. For example, the K-way partitioning we used in the Matisse library, which is commonly used for MPI and distributed workloads, but as far as we know, it has never been applied for GPU block forming. So we want to reorder based on reorder the threads. More specifically, we want to control how the CUDA blocks are formed, so that the data reuse is as high as possible. And that means a smaller amount of data needs to be loaded. And we can see that the airfoil mesh, the blocks in the airfoil mesh now look much nicer and much bulkier, much more data reuse. And this means that the data reuse increased from 2 to 3.6, and the bandwidth also increased by 40 gigabytes per second. One other thing to consider is that the layout of the data in memory. We usually do structured arrays layout when using parallel codes because when the threads are reading the first component and the second component of the data points, then it will have nice colored access. But it's only as simple as that when you're using global coloring, because when you're using hierarchical coloring or two-level coloring, when you're loading into shared memory, the order of this loading is independent of the order that you're doing the computations in. What you want to do is to collect beforehand all of the data points, all the indirect data points that you want to load, and then order them based on memory locations, and then you have as nice, an optimized, almost coalesced access. And this can be seen in the airfoil example. The SOA layout only improved on the global coloring on the right, but the best performance was achieved with the AOS layout with hierarchical coloring and the partitioning method. Now the problem with high data reuse is that it correlates with the higher number of thread colors. And especially in the case of Lulesh, which is a three-dimensional, highly connected mesh, and the colors are originally so the original mesh. The colors of the original mesh are high, and partitioning made it even worse. And the occupancy, the achieved occupancy with Lulesh is also quite low. It's about 20%. That means that there is nothing to hide the latency incurred by the added synchronization of the high number of thread colors. And that means that partitioning actually worsens performance. This can be examined more closely if we handcraft the blocks in Lulash, because Lulash uses a structured mesh, just an unstructured representation of it. So we could generate different shapes and size of blocks and analyze the thread color number and the reuse factor and their effect on performance. What we can see is that the last column, which was the result of the Matisse algorithm, achieved the highest number of thread colors. Actually, one more than it would have been necessary. But the best performance was achieved with only 4 colors and the highest data reuse within those number. Also, if you are caching into shared memory, you may want to determine what exactly you want to cache in. You don't necessarily want to cache in everything. Because, for example, mini-array accesses 2 data points indirectly and each have 32 double precision values. And after a certain block size, it just didn't run because of the increased shared memory requirement. Mini-array used, the original code of mini-array used, depending on the configuration, either a helper array, which is the last column here, or or atomics, which is the normalization factor here, and we managed to get better performance than either of them. All in all, we managed to get performance increases compared to the original codes in all of our test applications. These improvements ranged from 10% to 140% increase in performance. We did this by using the shared memory, 2-layer coloring, and this new reordering algorithm based on partitioning, which of course can be and should be further developed, for example, by taking into account the effect the high number of thread colors has on the performance. Thank you for your attention.
Thank you very much. Okay. I didn't catch that. Are these meshes dynamic or static during the calculations?
These are static.
And if I would have a problem that would require a dynamic mesh, and I would need to recalculate these colorings, how big cost that would incur?
The coloring algorithm is not. That's not the slowest part. The partitioning is the one that's slowest. And I think it's quite high. That's why I put efficient partitioning code also as a direction of future research there. So at the moment, no, it's not really feasible.
Okay. Further questions? I would have another question, maybe to both of you. So you mentioned that you are using this in a kind of fluid mechanics or fluid system simulation or something like that.
Yes.
How is it related to physics, and what is the proper topic what you would like to apply this for? So what is the application? I mean, this kind of routines and the whole development is what for in physics-wise?
So, for example, what the airfoil, the one I mention most often, is basically simulates. Well, it's also sample code, but it simulates the flow of the airfoil simulation.
I would be more interested in if you have any specific things what you have already working on from the physics side, and you would like to use this algorithm in order to improve the calculations. So do you already have bottom up or up bottom? That's the question.
So do we have any real world applications that do we have any?
No, I mean the aim of your development is just because you want to learn more and improve this kind of algorithms, or do you have a specific reason to develop this? That's
well, there is this library that Daniel was talking about. Is called OP2, and I think there are several real-world applications that are using this.
But not from your side.
But I don't. No, I'm not using it. I'm only developing it. Yes, yes.
That would be the question.
Yeah,
okay.
Sorry.
Thank you very much. Any further remarks or question? No. If no, let's thanks again.